So for this video, we switch gears just a little bit. We need to talk about how manipulating reactions affects the equilibrium constant. So this is something that will come up kind of at odd times. So what we're talking about is that manipulating the reaction means, what if I have a reaction, I know an equilibrium constant, but what I actually need to work with is the reverse of that reaction. Or I want to know what happens if I do a whole bunch of reactions in a row, right? You know that you can add the reactions together, just like it's an algebra problem, but what does that tell you about the equilibrium constant of the overall reaction when you get to the end of it? So we're going to talk about, if you do this to the reaction, this is what you do to the KEQ, and then we'll look at one example that goes with it. So if you reverse the reaction, you invert the KEQ, right? So just a reminder, invert means 1 over the original KEQ. So I have a little bit of a proof for you in case you would like to see this proved algebraically. If I have the reaction A plus 2B in equilibrium with 3C, I'm going to compare it to the reverse of this reaction. So 3C in equilibrium with A plus 2B. And I independently write the equilibrium constants for these two reactions. The one on the left, C is my product, so I've got C cubed in the top over A times B squared. This one on the right, A and 2B are my products, so I've got A B squared over C cubed. So if you take these and compare them, right, all I did was flip the equilibrium constant expression when I reversed my reaction. So if you had a value for the equilibrium constant for the reaction on the left, you could get the value for the reaction on the right by doing 1 over the value for the one on the left. Okay. The other thing that we might do is multiply a reaction by some value. So it's usually going to be a whole number, right? Because we like our reactions to have whole numbers. You might divide by a number, and we would use, if you multiply, say it was divide by 2, you would say multiply by 1/2. What you do is you take k to the n power to get the new value. So I've got a little bit of a proof that requires some algebra remembrances to get through. We're going to use this starter, A plus 2B, in equilibrium with 3C. We already have an equilibrium constant expression for this one. So C cubed over A times B squared. And we are going to compare this to, well, I've got N times A plus 2N times B in equilibrium with 3N times C. So whatever number that N has to be, this equilibrium constant expression is now C to the 3N over A to the N, B to the 2N. So every exponent has this n factor in it, so you can factor that out. So this would be the same as concentration of C cubed over concentration of A, concentration of B squared, this whole thing to the n power, which means for the value, I could take the original KEQ and then take it up to the n power. And the last thing that we might do is add reactions together. And if you add reactions together, you multiply the KEQ values. So let's say I had A in equilibrium with 2B, and I add that to 2B in equilibrium with 3C. When I add my reactions together, well, A plus 2B in equilibrium with 2B plus 3C. My 2B's would cancel out because I have them on both sides. So A in equilibrium with 3C is the reaction that I want to know the equilibrium constant for. So if I have, let's label this top reaction in purple, the bottom one in blue. So my top reaction, the purple K, is B squared over A. The one for the blue reaction is C cubed over B squared. And this one for my result reaction is C cubed over A, which, if you take a look back at these top two, if I multiply these K's together, I get the expression that I have below. So let's actually write that out. B squared over A times C cubed over B squared. B squared in the top and bottom will cancel, and I'm left with C cubed over A. So if I multiply the value of the purple KEQ by the blue value, I would get the value for this reaction. Okay, so let's do one quick example of this, and we'll try to make it a real example. So we are going to calculate the equilibrium constant for the reaction NH3 gas in equilibrium with 1/2 N2 gas plus 3/2 H2 gas if we know that the reaction N2 gas plus 3H2 gas in equilibrium with 2NH3 gas has an equilibrium constant value of 5.6 times 10 to the 5th at 25 degrees C. Okay, so what we have to do is compare, we'll say, put a black star by the original and put a green by the one that we are looking for. So compare the green reaction to the black reaction. What did we do to get from the black reaction to the green reaction? So get from the, we'll say, original to the unknown. So in the original, I have N2 and H2 on the left. In the unknown, I have N2 and H2 on the right. So first, and I mean, this actually doesn't have to be the very first thing that you do, because all of our options are multiplication type operations. So we could actually do this in any order we wanted. So if this wasn't the first thing you saw, that's okay. You could do it in a different order and get the same answer. But the first thing that I noticed was that we reversed the reaction. So the reverse of the reaction, right? If I have 2NH3 in equilibrium with N2 plus 3H2, if I reverse the reaction, I invert the KEQ, this reaction has a KEQ that is 1 over 5.6 times 10 to the 5th. I'm just going to leave that value the way it is, put a little parentheses around it. From here, to get to the reaction that I want, well, I'm at 2NH3, 1NH2, 3H2. The unknown has 1NH3, 1/2 N2, and 3/2 H2. So when you first look at it, you might immediately say divide by 2. But we don't have a rule for dividing by 2. We do have a rule for multiplying by 1/2. So if I multiply by 1/2, which is how I get NH3 in equilibrium with 1/2 N2 plus 3/2 H2, I need to take the KEQ from step 1, which was 1 over 5.6 times 10 to the 5th, and take it to the 1/2 power. So I will invert it and then take the square root of it. So the KEQ for my unknown final reaction, which is the one that we put a green star by above, if you plug all of this into your calculator, you get 1.3 times 10 to the -3rd.